Hey everyone! Let's put on our cosmic detective hats today because we are investigating a seriously fascinating astrophysical mystery. We're looking at Caldwell 38, which is this absolutely spectacular structure known as the Needle Galaxy. But we aren't just here to admire how pretty it is. We are hunting for the invisible forces, specifically the electric and magnetic fields, that literally shape its entire architecture. And our main goal? We're trying to solve the mystery of its missing halo. So, meet Caldwell 38. It's a gorgeous spiral galaxy located out in the constellation of Coma Berenices. And what's really cool is that because we view it perfectly edge-on from our perspective here, we get this unparalleled look at its vertical structure. We can clearly see its bright central bulge and those dark dust lanes slicing right across its galactic disk. It is pretty much a textbook example of a spiral galaxy, actually a lot like our own Milky Way, which makes it the absolute perfect laboratory for our investigation today. Now, to truly appreciate the scale of what we're looking at, we have to grasp the sheer distances involved. This majestic star city sits about 38 million light-years away from our vantage point on Earth. Think about that for a second. That means the light hitting our telescopes right this very moment actually left that galaxy 38 million years ago. It's a vast cosmic gulf, for sure. But despite that immense distance, modern radio astronomy lets us peer right into its invisible ecosystem today. Which brings us to the central mystery of our explainer. When astronomers point highly sensitive radio telescopes at most edge-on galaxies, they usually find these massive, billowing halos of radio emission that extend thousands of light-years above and below the galactic disk. But Caldwell 38? It's strangely different. Its radio halo is incredibly thin. It's just tightly compressed right up against the disk. So why? What exactly is keeping this giant galaxy so neatly tucked in? When we compare the visible starlight from the optical spectrum on the left to the compact radio continuum emission on the right, the puzzle becomes super clear. Just look at how stretched and flattened that radio signature is. It has a vertical to radial ratio of just 1:6. It's consigned, it's flat, and it just stubbornly refuses to billow out into the cosmos like we'd expect it to. Okay, let's dive into Clue 1, cosmic rays and starbursts. To really understand that flattened radio signature we just saw, we need to talk about cosmic ray electrons, or CREs. You can think of them as high-energy microscopic travelers. When massive stars explode as supernovas, they act like gigantic particle accelerators, just blasting these electrons outward at near light speed. And as these electrons travel and spiral around the galaxy's magnetic fields, they emit synchrotron radiation. That's essentially a specific type of energy glow caused by particles moving in a magnetic field, which our telescopes pick up as radio waves. Now, usually, it's these violent supernovas that provide the raw energy needed to pump cosmic rays high up into the galactic halo. But here's the catch. Our investigation reveals that Caldwell 38 is what astronomers call a quiescent galaxy. Basically, it has a very low star formation rate. Without a bunch of new, massive stars exploding, the engine driving this galaxy is just weak. The cosmic ray electrons we do manage to see are actually part of an old population, roughly 100 million years old, that are just slowly, lazily diffusing away from the midplane. There's no violent starburst pushing them out into the void. All right, let's move on to Clue 2, the magnetic maze. We need to map the invisible highways these cosmic rays are actually traveling on, the galactic magnetic fields. And a stark contrast reveals itself when we look at a typical edge-on galaxy like NGC 891 on the left. It has a robust, strong magnetic field, which you can see by those warm red and yellow colors. But for our subject, Caldwell 38 on the right, notice all those cool blues and greens? That tells us Caldwell 38's magnetic maze is exceptionally weak compared to its peers. Now, you might be wondering, how do we actually measure the strength of a magnetic field 38 million light-years away? Well, astronomers use a really clever concept called equipartition. They assume that the energy from the cosmic rays and the energy of the magnetic fields are locked in a state of balance out there in the interstellar medium. By calculating this balance, they determine that the magnetic field in Caldwell 38 averages less than 5 microgauss. To put that into perspective, that is incredibly weak. We're talking barely a whisper of magnetic force. And this exceptionally weak field takes on a very specific shape. By tracking the magnetic field along our line of sight, using what's called a rotation measure map, we see this pattern of sign reversals across the nucleus, shown by the alternating red and blue patches. This actually reveals an axisymmetric spiral structure. So essentially, the magnetic fields are predominantly trapped running parallel to the flat galactic disk. They run along the disk rather than pointing up and out, acting almost like a lid that keeps those cosmic rays tightly bound inside. Let's zoom out to the fundamental physics for our next section, the prime mover, electric currents. To really crack this case, we need to bust a major, long-standing myth about how these cosmic magnetic highways are actually built. There's this common misconception out there that large-scale cosmic magnetic fields are created merely by the turbulent mechanical mixing of conductive fluids, kind of like stirring a giant cosmic soup, but basic physics tells us a totally different story. The absolute fact is, you simply cannot have magnetic fields without electric currents. As Donald E. Scott pointed out in his analysis of the Maxwell equations, magnetic fields cannot exist in the absence of the current density, J, which is their cause. Out in space, plasma is highly conductive, and it carries vast, invisible electric currents. It is the flow of these electric charges that actively generates and shapes the magnetic fields we're observing. So the crucial point here is that electric charge flows are the true prime movers. Main and secondary electric currents flow right through cosmic bodies, creating the magnetic loops and structures all around them. In Caldwell 38, the lack of powerful, dynamic electric currents flowing vertically out of the galaxy perfectly explains why its magnetic field is so weak and flat. The electrical engine is literally just idling. But just when we think we have the whole galaxy figured out, our investigation uncovers a twist. Let's look at a localized mystery. There's a strange anomaly in one specific part of Caldwell 38 that complicates our neat little theory. Focus on the faint yellow lines in the upper right. That's the galaxy's northeast quadrant. Instead of running parallel to the disk like the rest of the galaxy, there's a localized X-shaped magnetic field pointing away from the plane. And incredibly, this magnetic structure perfectly aligns with extraplanar gas we can see in soft X-rays and neutral hydrogen. Something is pulling or pushing the material out into the halo right in this exact spot. So what is causing this localized breakout? Well, our sources present two main suspects. It could be an internally driven, magnetically guided outflow. Think of it like the ghost of a past cluster of supernova explosions in that specific region, pushing hot gas upward. Or, alternatively, it could be an external gravitational pull from a neighboring companion galaxy, like the nearby IC 3571, physically dragging the gas and the magnetic field lines right out into space. Now, despite that small, localized mystery, let's wrap this up. The verdict? A benchmark quiescent galaxy. Let's bring all our clues together to finally close the case on Caldwell 38's missing radio halo. Why is it so thin? Well, it's a perfect storm of cosmic conditions. First, a low star formation rate means there is a very weak engine. There just aren't enough supernovas to blast particles outward. Second, this results in weak disk-parallel magnetic fields under 5 microgauss that trap what few cosmic rays there are. Third, Caldwell 38 is massive, meaning its deep gravitational potential heavily contains its own gas. And finally, all this leads to highly inefficient, slow transport of cosmic rays, moving at only about 60 kilometers per second. Every single factor conspires to trap the halo tightly against the disk. Ultimately, Caldwell 38 isn't just a beautiful galaxy, it's a benchmark that shows us exactly how galaxies behave when their internal engines power down. And it leaves us with a pretty profound thought to take away. Next time you look up at the night sky, realize that the empty blackness is actually humming with unseen, interconnecting electric currents and magnetic fields. It really makes you wonder, right? What other invisible electrical forces are out there silently sculpting the cosmos beyond the stars we can see? Keep wondering, keep looking up, and we'll see you in the next explainer.